Okay, welcome back. This is 4.7, optimization problems. Essentially, more story problems here. Um, what you're going to have are some restrictions and then a formula that you want to optimize. So you're going to be taking its derivative and then looking for the critical numbers and identifying the max and min and that sort of thing. So you'll be given, like I said, some sort of story problem, and then within the story problem there'll be restrictions, and you need to get rid of the number. You want the equation to be in terms of one variable, so you'll have to figure out how to reduce the number of variables. And you see these again later in Calc 3. They're the same kind of problems. So anyways, 4.7 optimization problems. The first kind of problem we'll take a look at is the area problem. Particular number 9. So it says find the length and width of the rectangle that has the given perimeter and a maximum area. Okay. So find length, width of rectangle with given perimeter with maximum area. Okay. So the book is giving you the perimeter is 80 meters. And this right here is essentially a restriction. We have some formulas associated with area and perimeter. So the area formula, we know, given some sort of rectangle, if this is x and this is y, then the area we could say is x times y. And this is the formula we want to optimize. Okay. Then you're going to have a constraint formula, which is the perimeter formula. And we know perimeter is 2 times x plus 2 times y. So this is a constraint formula. Okay, so using this information, we're going to reduce the number of variables in the area formula, and then we could take the derivative of this and try to optimize the area. Okay, so first I'm going to take this restriction and plug it into the constraint formula. I'm going to go ahead and solve for y. Okay. And then I'm going to plug this into my area formula to reduce the number of variables. And then I can take its derivative. Okay, so area is equal to x times y, but we replace y with 40 minus x. Okay, so once I get here, I can take a derivative. Let's first distribute. And now I'll take the derivative with respect to x. Okay, so identify the critical numbers. And we just get one critical number. Usually you don't have to go through the process of checking to see if it's a max or a min. In general, it will be whichever value you're after in these problems. But at first, you can verify the fact that this is going to be a maximum by doing your number lines and test values, the signs, and your conclusion. Right? So if we tried maybe x is 0, or rather, yeah, 0, sure, you'll get a positive from the derivative, so it's going up. Try x is 30, and in the derivative you'll get a negative, it's going down. So yeah, we have a maximum at x equals 20. Okay, so when x is 20, you'll get a maximum area. We need to then find the corresponding y value for the answer. We're trying to look for a length and a width of the rectangle. So y will equal then 40 minus 20. In other words, y is 20. So it looks like a square will have maximum area. With sides 20 meters long. Okay. Okay, so this is kind of the theme throughout all these problems. This part right here, again, you won't necessarily have to do this every time. In the beginning, you'll be worried about it, but then you'll see, oh, it's always going to be the answer thereafter here. And so you'll sort of kick it to the side unless your job depended on it or something more important like that. Okay. Okay, so that's the idea. Let's see what else kind of problems we have in the book. So we'll just go through a whole bunch of examples here. This is 21, the Norman window problem. So a Norman window is constructed by joining a semicircle to the top of an ordinary rectangle window. Find the dimensions of the Norman window of maximum area when the total perimeter is 16 feet. All right, so you have this constraint given, but let's think in terms of all right, so what is a Norman window? Maybe I should explain that first. This is our Norman window. So it has a semicircle on top of a rectangle, and they're telling us in the book, they give us some of the dimensions. They want this dimension to be x, and then they want this to be y. And they're saying the radius of the circle is x over 2. Okay. So this distance is x over 2. Okay, the total perimeter, your walking distance around the window is going to be 16 feet. And what we're after then are those two basic equations, the optimization equation and the constraint equation. So what are we trying to optimize? Well, area. What is the constraint then? The constraint is going to be this perimeter, which is given at 16. So we need a formula for perimeter and a formula for area. So first we'll go after the formula for perimeter. And that's just walking distance around this object. So I'll have 1x, 1y, and then half the circumference of a circle, and then another y. Okay? So I'll have 2 y's, 1x, and then 1/2 the circumference of that circle. The circumference is 2 pi r, so 1/2 2 pi, and the radius we said is x over 2, so times x over 2. We know that this thing equals 16. That gives us our constraint equation. Okay, so 16 is 2y plus x plus, what happens here? We get rid of one of the factors of 2, and then we get pi x over 2, pi over 2 x's. We may want to rewrite that character, because we're going to be using this as 1 plus pi over 2 x's. Just factor out the x. Okay. I also need an area formula, so let's worry about the area. The area will just be the area of this rectangle, which is length times width, which is x times y. And then we have to add in the area of the semicircle, which is 1/2 its area. So 1/2 times pi r squared, where r is given by x over 2. Let's clean that up. So I have xy plus, what is this going to be? 4 times 2 is 8, so pi over 8 x squared. Okay, so that's my area formula. Now I'm going to reduce the number of variables using this formula here. Okay. So I'm going to solve this formula for y and then plug it into the area formula. So I have 2y equals 16 minus, I guess, 1 plus pi over 2 x's. Then I'm going to divide both sides by 2, which is essentially the same as multiplying by 1/2. So you end up with y equaling 8 minus, and then if you distribute 1/2 plus pi over 4 x's. So now I can plug that into my area formula. And then I'll be able to take the derivative of that thing. So you use the constraint formula to reduce the number of variables, then you take the derivative of the optimization formula. Okay, so I have x times this thing, x times y, plus pi 8 x squared. So the most annoying thing about these problems are the constants, I guess. Let's clean it up just a little bit. So I'll go ahead and distribute the x all the way through. I have 8x minus 1/2 plus pi over 4x squares, then plus pi 8 x squared. Okay, if we want to, we can sort of combine these two guys together by adding their coefficients together. Okay, so we'll have minus 1/2 minus pi over 8 minus pi over 4 minus pi over 8. So pi over 4 is the same as 2 pi over 8. So minus 2 pi over 8 plus 1 pi over 8 is minus pi over 8. So I end up with minus 1/2 plus pi over 8 x squared. And then I can take the derivative. So I have 8 minus 2 times 1/2 plus pi over 8 x. And then I'm going to distribute that 2 and set it equal to 0 so I can optimize the thing. So 8 minus 1 plus pi over 4 x's. Set it equal to 0, so x times 1 plus pi over 4 equals 8. And then divide by 1 plus pi over 4. And of course, we hate complex fractions, so I'm going to multiply top and bottom by 4. Okay, I'm going to take, I need the y value as well for the other dimension of my Norman window. So I just look for an equation that has y in it, and then I'll substitute this expression in there. So let's take a look at that. I'm going to find a common denominator here. It's a weird problem. So 2 plus pi all over 4 times 32 all over 4 plus pi. 4 goes into 32 8 times. Okay, so we can distribute y equals 8 minus 16 plus 8 pi all over 4 plus pi. And get a common denominator. So we have 32 plus 8 pi all over, minus the 16 minus the 8 pi all over 4 plus pi. And then finally 32 minus 16 is 16. 8 pi minus 8 pi is 0, all over 4 plus pi. So ultimately our dimensions, we want y to be 16 all over 4 plus pi, and I guess we're in feet. And then here x equals 32 all over 4 plus pi feet. Okay, let's look at 25. So in 25, they're giving us a formula as a constraint. They want maximum area. So a rectangle is bounded by the x-axis and the semicircle y equals square root 25 minus x squared. What length and width should the rectangle have such that its area is maximum? Okay, so this becomes, I believe, our constraint formula. And let's take a look at the picture. So here's the semicircle. It's actually the graph of this. And then we're putting a rectangle in here. And we want the rectangle to have a maximum area. Okay, so the formula, we're trying to optimize them, and this will be our constraint. But we're trying to optimize the formula, area equals base times height. And we want to put this area formula in terms of, I guess, x's and y's, right? So the base of this formula, if this length here, if this point is x comma y, the base of the rectangle is actually 2x. Okay, so there's 1x here and then there's 1x here. So the base is 2x and then times the height, which is y. Okay. Then to reduce the number of variables, you use the constraint formula. So I got 2x times the square root of 25 minus x squared. And then this thing becomes the formula we want to optimize. Okay, so let's go ahead and do that then. So area is given by this thing. It's 2x times the square root of 25 minus x squared. Okay, looks like a bit of a headache, but that's okay, we can handle it. Right, it's going to need a product rule and some chain rule. So if I leave the 2x alone and then take the derivative of this, we'll have 2x times 1/2 times 25 minus x squared to the 1/2 minus 1 is negative 1/2, and then the chain rule says I have to multiply by the derivative of this, which is negative 2x. And then plus, take the derivative of 2x, which is just 2 times, leave this part alone. So 2 times the square root of 25 minus x squared. Let's clean it up. Eventually we want to set it equal to 0, so I'm going to find a common denominator between these two terms along the way. Anyways, 2 times 1/2 is just 1. I have a negative 2 in the numerator times x squared. In the denominator, I have the square root 25 minus x squared. And then plus 2 times the square root of 25 minus x squared. I can rewrite the second term as 2 times 25 minus x squared over 1, and then multiply it top and bottom by the square root of 25 minus x squared. So I'll have negative 2x squared plus, well, when I go this times this, the radicals will go away, and I'll just have 2 times 25 minus x squared, which will be 50 minus 2x squared. Of course, this is all over the square root of 25 minus x squared. And then that'll be negative 4x squared plus 50 all over the square root of 25 minus x squared. Okay. To set that equal to 0, there are some critical numbers at 5 and negative 5, but if you think about the picture, in those cases, there's not going to be a rectangle. At 5, when x is 5, the height of the rectangle will be 0. Okay, so that will just be a line, and that doesn't make any sense for us. The area would be 0 anyways, so we don't want those answers. We'll just take the place where the numerator is equal to 0. So negative 4x squared plus 50 is 0. We have negative 4x squared is negative 50. So x squared is 25 halves. And take the square root of both sides. So x is plus or minus 5 root 2 over 2. And obviously we want the positive answer. If you think about the geometry, we want this answer, okay, not this answer. And then for the y value, we could just take this thing and plug it into our y formula, which was the constraint formula. So y equals square root of 25 minus x squared. Of course, x squared is 25 halves. X squared is 25 halves. 25 minus 25 halves is just 25 halves. Right? And then that's also 5 root 2 over 2. Okay, so the dimensions of the box, you want to be a little careful because the rectangle's dimensions is actually 2 times x, if you remember, for the base. So the base is going to be 2 times this thing, so 5 root 2, and then the height is just y, so that'll be 5 root 2 over 2. And these answers are in feet. Okay? Okay, when we go the optimized distance, what we're going to end up doing is squaring to get rid of these roots. So you see in this example, the roots are kind of a big headache as we go through the problem. And to deal with all these square roots. It's never a fun day. So in general, when you deal with distance, I'm not sure which numeral I'm on. I'll say this is 3. You're dealing with this square root formula, right? So it's x2 minus x1 squared plus y2 minus y1 squared. What we're going to do is instead optimize basically this thing squared. So optimize the function f of x, which will equal just x2 minus x1 squared plus y2 minus y1 squared. So in particular, let's look at number 15. And we have the function g of x equaling the square root of x. And we want to find the point on that graph. So this is kind of our constraint. such that the distance from this point to this graph is a minimum. Okay. So if you need to, you can kind of graph the thing. 1, 2, 3, 4. Just got 4. At 1, it's 1. At 4, it's at 2. Okay. Here's the point for 0. And it's not entirely clear if the minimum distance is really the perpendicular, this perpendicular kind of distance right here. It could be that the minimum is over here a little bit. Maybe it is actually at this perpendicular distance. Maybe it's a little bit over here. I don't know, right? So we can use this optimization technique to figure that out. And so what are we doing? We have our constraint formula, square root of x. The thing we're optimizing, we're just going to use the square of the distance formula. So we use this thing. And so what is that? F of x in this case, we have, and we'll use this as our x1 comma y1 coordinate. So we'll plug this point into this formula. And so we'll have x minus 4 squared plus y minus 0 squared. So I'll have x minus 4 squared plus y squared. And then I want it to be completely in terms of x. Okay, so I can find the derivative and all that jazz. So you use a constraint formula to reduce the number of variables. So we know y is equal to the square root of x. So I can just substitute that into here. So I have x minus 4 squared plus square root of x squared. In other words, x minus 4 squared plus x for my formula. And then that's the thing I'll take the derivative of. So power rule on that part, 2 times x minus 4 plus 1 equals 2x minus 8 plus 1 is 2x minus 7. Set it equal to 0. And you get 2x equals 7. And then x equals 7/2. Okay. So almost at 4, right? It's 3.5. It's actually this point right over here where the distance between the point and the graph will be minimum. And so the corresponding y coordinate then would be square root 7 over 2. So the point to minimize distance is going to be 7/2 comma square root 2, 7 square root 2 over 2. Sorry. Sorry, it's plugging 7/2 of square root, crud. Jeez, having a day. Square root 14 over 2. Jeez. Okay, let's look at one kind of engineering or question. So beam strength. A wooden beam has a rectangular cross section of height h and width w. The strength S of the beam is directly proportional to the width and the square of the height. What are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Okay, so it's 37. I have this log, and we're trying to get a board from it, I guess. There's this rectangle here that they're cutting it. Trying to cut from it. It has a width they're giving by the dimension w, and a height, this length, they're given by h. And then the diameter of the log, so from this point to this point, they're saying is 20. They're also saying the wooden beam has a rectangular cross-section of height h and width w. The strength of the beam S is directly proportional to the width and the square of the height. So directly proportional, you're going to put a constant k, and then the width times the square of the height. So you would write out that formula in that way. Usually they'll have, if you don't remember how to set up these kind of problems, they go through it in algebra classes. They have these proportionality. So you have inverse proportional, directly proportional, that sort of thing. And usually in college algebra, we'll go through that. So you may want to pick up a college algebra book and just review if you don't remember. Anyways, this is the thing we're trying to optimize. What are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Okay. So the diameter we're going to be using here, well, the restriction, which may not be obvious, could be found by relating these two variables using the Pythagorean theorem. So you could say w squared plus h squared is equal to 20 squared. And if we use this as a restriction formula, we can definitely reduce the number of variables over here. Of course, k is just a constant, so we won't be removing that. It's the w and the h that we're looking to reduce. So I can sort of get rid of the h squared. That'll be 20 squared minus w squared, and plug that into here. So that'll make S equal k times w times 20 squared minus w squared. And I want to find the dimensions w and h that optimize the strength, maximize the strength. So this is my formula. Let's go ahead and distribute. So you'll have 20 squared k w minus w cubed, k times w cubed, and then take its derivative, set it equal to 0, etc. So S prime is 20 squared k, derivative of w is 1, minus, bring down to 3, so power rule, 3k w squared. Okay, we'll set that equal to 0. And you'll see that k really doesn't make a difference. So this constant is going to just divide out. Okay, so I'm going to add this over. 3kw squared equals 20k, it's 20 squared k. Divide both sides by 3k, and w squared equals 20 squared all over 3. And then take the square root on both sides and get w equals 20 square root 3 over 3. And then we can back sub this into this formula here. So h squared is going to be 20 squared minus 20 squared over 3. So h squared is 220 squares over 3. And then take the square root on both sides, and h will be, so what are we going to have? 20 square root 6 all over 3. Okay, the units are inches. Okay, that's pretty much it. We'll see you next time.